Hello, thank you for joining the Spec Innovation Summer Intern Special Webinar. Our interns have been hard at work this summer and are excited to show you what they've been working on. They will be showing their work with the Microsoft HoloLens, unmanned aerial systems, research, and more. They have made a considerable impact in the development and improvement of our model-based systems engineering and requirements management tool, Innoslate, plus our new standard operating procedure NLP tool, Sopatra. Since this is a recorded webinar, send us your questions through the Innoslate users group on LinkedIn or email us at info@specinnovations.com. First, let's get to know our interns and presenters for this webinar.
Hey everybody, my name is Amir Abrari. I'm a summer intern for system engineering at Spec Innovations. I go to George Mason University and I'm an accelerated master's student in system engineering.
Hello, my name is Dominic Galarza. I'm also a summer systems engineer intern here at Spec Innovations. I also go to George Mason University and I'm an accelerated master's student in systems engineering.
Hi, I am Lily Stevie. I am a systems engineer intern at Spec Innovations. I am currently wrapping up my master's in system engineering at George Mason this December.
So to begin our work in Spec Innovations, we were introduced to the Counter Unmanned Aerial Systems project, sponsored along with Dan Coleman with the Wicked VUCA framework. Our counter swarm project had the objective of preparing for various counter drone operations. The Biden administration pushed to enhance counter swarm unmanned aerial systems and implemented the Wicked. We also wanted to implement the Wicked VUCA framework to our project. So we started this project from the scratch. Was a huge development in our team with Dom and I, and built a lot of confidence in our work and understanding the many facets of system engineering. With the guidance of Steve Dam and Michael Jordan, our supervisor, we were able to have immense control and effective contributions to the overall project. In terms of the progression of the project, we researched swarm UAS to understand the system, researched counter UAS technologies, strategies, and tactics, researched and documented aviation laws, created documentation of multiple task reports, created mission and functional requirements, and traced those functional and mission requirements to many more requirements or validations or test suites, completed an analytical hierarchy process for the UAS drone demonstrations, and started working on a proposal for our potential stakeholders in entering phase 2. So to start our counter UAS problem, we were faced with 3 different behavioral focuses that we had to focus on and try to disrupt as counter UAS. The 3 ideals were to communicate locations to avoid collision with neighboring agents, which is within the swarm, that's how the behavior is, communicate flight directions within the swarm, and maintain equal distance from each other. These 3 ideals are 3 of the most important facets that a swarm controls by itself to be able to direct each other, to be able to move within different locations. So what we ended up doing, we made our own behaviors, and through our research and through our own structure, we made sure that we have all the 3 behaviors summarized into 3 different entities: navigation, spatial organization, decision-making. And within these, we categorized them and had a lot of description on what they are, sourced them back to the main source, and made sure that we consider all 3 of these facets. We had to understand the swarm itself and its behavior, and given our timeline, we were able to understand the system and create an architecture to work off of. And by building this, it helped us understand our requirements and constraints for our project. And we were also able to later on in the project trace our requirements back to the swarm behaviors to stay within the scope of our project goals, because we were told from the very beginning that we have to disrupt these 3 behaviors. We had the ability to make many different diagrams from the same database, which allowed us to have supportive diagrams and documentations, such as creating and having this diagram over here and making it into a spider diagram and showing it to our stakeholders and showing them many connections with the tracings and such.
We've done extensive research on the technologies available to counter swarms of drones and divide them into 2 main categories: detection and aggression, as you see on your right hand. Detection consists of equipment to overall spot or pick up on hostile drone activity. The second main category, aggression, are measures to neutralize drones that are already in the air, which we divided further into two subcategories, destroyers and jammers. As in the name, destroyers will completely destroy a drone, while jammers will interfere with key communication components within the drone to force it to land on the ground. We then expanded this idea by creating a traceability matrix to trace identified advantages to the counter technology to each specific component. As you can see to the graph on your left, each counter equipment will have an X, which means that that specific equipment is associated with a respective advantage. The more X's that a piece of equipment has, the more advantages it has over its options.
The analytical hierarchy process is a subject that I myself will be learning in this upcoming fall semester at George Mason University. But during my internship here, we used the original AHP documentation provided by Spec Innovations that was used for the Lunar Rover project to make critical decisions in practice for our Wicked VUCA project. This practice allowed us to choose the most ideal and optimized decision based on how much we value each of the 7 criteria. You can see the 7 criteria on each of these graphs, and we can see the scoring in the very top graph on the left. On the very left, we have a graph that shows 1s, 3s, 1, 1 over 5, and this scoring indicates, and later on indicates our eigenvalues that we calculate. Using these eigenvalues and assessing our important weights for each criteria, we can use the eigenvalues and the weights to create quantitative reasoning to why one alternative is better than the other. The bar graph displays each criteria one by one and the total accumulation of weighted scores that help us conclude our most ideal options. Out of the 3 most ideal options, we decide on the DJI Tello EDU, meaning that through all 7 criteria, we had our scorings accumulate and show us that the most ideal alternative is that one.
So next we move on to talking about our NASA STTR project. For this project, our whole goal is to create a digital assistant within Sopatra to go over SOPs, which are standard operating procedures. These are most often used for airlines. And so we have created with a team at George Mason this diagram of the steps that need to be completed for a whole life cycle of an SOP. So for Sopatra, we are focusing on the creation of SOPs, which involves editing, and the simulation and analysis of SOPs, and the publication of SOPs. So this is stuff that we have been working on in individual pieces, and we'll hopefully get into Sopatra in the future.
So during our tenure at Spec Innovations, we've also been focused on learning Microsoft's augmented reality, or AR, headset, HoloLens 2, and understanding its features. We were tasked with operating the HoloLens 2 and understanding the ins and outs of this equipment to help drive the technology forward. This allowed us to have new learning experiences with the AR world and its applications in the real world. Here's a demonstration of me using the HoloLens and showing its capabilities by using the software. And so a couple of things I'll say while the video is playing is that while in the video my hand appears behind the screen, that's not actually the case while using the headset. The screen appears right before you, and you touch and do whatever you want as if it were a physical screen. There is a slight learning curve to be able to effectively use a headset and navigate quickly. However, once you spend some time and get hang of precisely touching the screen, everything else will fall into place. It was honestly really cool being able to experience this kind of technology for the very first time. And upon getting more experience and comfortable with the headset and this technology, it really opened my eyes to the true potential of how augmented reality can impact the world and change how this industry operates. Right, so you've seen the current state of AR technology and its potential. Now we want to showcase the desired future of what AR can accomplish. As time progresses and AR technology becomes more advanced, we hope to see the headsets, like the previously seen HoloLens be applied in real-world aviation. Our goal is to have the pilot be able to put on an augmented reality headset, as seen on the left, and within the headset, have them open a standard operating procedure, or SOP, and have that SOP be read out loud to the pilot while each step is displayed, all hands-free and commanded simply by using their voice. A future implementation is to have the headset highlight each specific lever or button the pilot will need to push when the step requires them to do so. We've created diagrams and documents highlighting the process of how pilots will interact with the technology, including the second picture to your right, which displays what pilots will see when they use the.
Now that we've gone over how the NASA project and the SOPs can contribute, and SOPs and the mixture of AR within that can contribute to the overall success of the NASA project, we want to show the exploration and the extensive research that we have done within the AR world to better our understanding and make ourselves and prepare ourselves for a better future with AR exploration. We've created various timeline mappings to show stakeholders potential upcoming technologies that could improve our project. Although HoloLens 2 is a very, very advanced lens and AR feature, it's full of AR features, it is yet limited to many different things, and that's why we've also documented many different problems and issues that we want to present to Microsoft and better their product as well. So as you can see here, we created our timeline diagram for future AR acquisitions. The NASA project and the use of HoloLens 2 showed the extensive ability of virtual machines to complement our reality and enhance our work. With AR and VR being the clear future of training and advanced labor, it was very important to us to be aware of the other technologies available and to document them appropriately. And during that tenure at Spec Innovations, we've continuously been researching these glasses and making sure that we understand their features as good as we possibly can. So when these products come to the market, when they're available, we can get our hands on them and test them and use it to the best of our abilities.
All right, so now let's switch gears to some of the Innoslate projects that I personally have gotten to work on and contribute towards. So one of the first projects that I was placed on was to research SCXML, which is the state chart XML, which provides a state machine-based execution environment based around Herald. So the purpose of this was to eventually implement machine execution into Innoslate. And I spent a lot of time researching XCXML and the implementations of it and other state machine execution tools. And from there, I ended up comparing Innoslate's current state machine diagram to the SysML standard of the state machine diagram, and identified a lot of missing elements and things that just needed to be added to get it to where it needed. And then from these missing elements and all the research I did, I created requirements to improve it, the state machine diagram, and even to add state machine execution to the Innoslate. And since then, the state machine execution has kind of been put on the back burner for Innoslate, but we have plans to implement an improved state machine diagram, and I have since then refined the requirements for it for the next version of Innoslate. So on the left and on the bottom, you can see the current state of Innoslate's state machine, which is very simplistic and just has the initial node, the final node, and a state. But it's missing a lot of things like a history node, parallel states, composite states, actions within states, and actions and guards on transitions. So on the far right, there's a wireframe for what will hopefully be the next step in the state machine diagram in Innoslate. So this is a project that I got to work on as well that actually got implemented for part of it into Innoslate, which is Intelligence View. So in the upper left, you can see the original Intelligence View that was not user-friendly. If you had a lot of information and data that populated into Intelligence View from the tests, it was very clunky and you could scroll for hours and it was not user-friendly. So Intelligence View purpose is essentially to query the database in Innoslate for different tests for quality, connections, traceability, missing information, just to see how well the project has been created overall. So some of the improvements that were made were taking those long lists of data in the original intelligence view and turning them into widgets so that you could pick and choose what you wanted to see, and even adding in drop-down features and minimization features, and also adding charts of the analysis to it. So on the bottom right, you can see the bar analysis widget that has a bar chart of all of the count of errors and the count of warnings that were flagged in the actual running of intelligence view. And then the overall analysis widget shows you the percentage of tests that were passed. And this one is a 52%. So it would definitely be worth the time to go through each of the tests and see what were flagged and maybe fix them and go through the project from there.
Thank you, interns, for presenting. We would like to thank you for joining us today. We hope you can join us for our next live webinar, Dissecting SysML 2.0. Be sure to check your email for the invitation. We also encourage you to visit our website, check out our books and blogs, and connect with us on social media. This concludes today's presentation. Thank you again for your attendance, and we hope to see you again at our next webinar in September. Please enjoy the rest of your day.